university as an undergraduate, chemistry with a major in mineral processing, then decided to do a PhD at the JK, choosing a topic that he was sure he would never use again. So he had quite a different approach to choosing a topic. Then he can be finished with his PhD and move on with his life, which he's done. I met him there, and it was the wonderful D who said, oh, you know, we can't let Grant lead, he's too good. And then I was the one who had the funding through the Anglo Centre then, so Grant ended up working with me instead of D. So he did a bit of work with D, but mainly land up in my arena, and that's where this whole getting into the energy assessment came. A couple of people tried it a bit, and Grant really took it by the horns and took it way beyond my expectation. And Grant has all the hallmark of a really good employee. He never agreed with anything I said. So that's an important part of being a researcher. If you keep agreeing, well, you're just going to carry on perpetuating the errors of the past, you know. So him and Ben had a good partnership of arguing about everything with me. And it's been great because we all learned through the process, you know, to push the boundary. And I hope you're still doing that at Azenco, not agreeing with anyone. So
very disagreeable.
Grant can bring another disagreement to the world to the fore. But based on good thoughts and good science of where to go to next and not be stuck in what we've been doing in the past. So over to you, Grant, and thanks for joining us.
Thanks, Malcolm. Thanks for the introduction, and thanks for the opportunity to present. This is something that I actually pulled together for an internal presentation at Azenco to our comminution group, and I've kind of expanded it a little bit and put in a bit more interesting researchy type things at the end, but it kind of spans a number of years of work that I've done, and numerous people on the call today, Malcolm and Marco and others, have looked at in the past. But something that I'm quite passionate about, and it's funny how often you actually see these P80 being misused, or interesting things about the slope of particle size distributions when you actually start to understand it. So that's what I'm going to talk to you about today. The picture on the right there, for those who were discussing it earlier, was one of my first interactions with the GCC at doing a survey in South Africa at Mogalakwena mine, and yeah, loved working in the GCC and learning from people from a diverse background and of experiences and cultures, and yeah, it's been really great, and I'm very proud to join on as a member this year. So yeah, looking forward to bigger and better things ahead, and being able to travel again would be good as well. See you all in person. So the first place to start when we look at P80, I think, is Bond. I think Bond formalized this use of P80, and you could see a couple of quotes there on the right hand side. So the reason he, or at least from what you can glean from his writing, the reason P80 was chosen as a marker size for describing a size distribution is that it was the point where the curved portion of the plot tended to end, and the linear portion started to occur below that. So P80 was where the coarse end of the size distribution started to conform to a linear relationship in log space. And he also talked about the fact that the slope of that relationship in a log-log plot, like the one on the left-hand side, was typically about 0.5. But he did say that it can get may approach unity. But a lot of the equations that he actually pulls together, he talked about the fact that actually his equations are only valid when the size distributions are parallel in log-log space and have that slope of about a 0.5. And you can see this on the graph on the left-hand side here, where the typical circuits that were kind of being used in the time of Bond in the 50s, where you have multiple stages of crushing, rod milling and ball milling. They did tend to, and they still do tend to have parallel size distributions that have a slope of about a half in log-log space. So yeah, his work is very valid and actually has stood the test of time. And I think we need to acknowledge that as well as acknowledging the potential failings and shortfalls of this technique with with different comminution devices that are around today. So if you look at comminution today, a lot of the circuits are sag and ball mill circuits, and you get these size distributions like the one that I'm showing here. Once again, we're in log-log space, and the primary crusher product and the cyclone overflow tend to have that slope of about a half in log-log and tend to be parallel. The real problem arises with the sag trommel undersize, which is the transfer point between the sag mill and the ball mill. And the use of P80 here or T80 on the transfer size has been shown to be flawed many times. And I think some of the work by Morel is really good to read on this. I think he goes into quite a lot of detail. So if you use this T80 on the transfer size, it actually results in a much coarser size distribution than you'd expect from the amount of fines. Or put another way, the amount of fines is much greater than you'd expect with that T80 if the slope of that line was parallel with the primary crusher and the cyclone overflow. So what that results in is that the work done by the mills can be described using the 80th percentile passing, but it's only valid when the size distributions are parallel in log-log space. And the reason that the size distributions aren't always parallel is due to differences in classification, breakage mechanisms, particle selection processes, and they can result in these non-parallel size distributions with more modern equipment like the sag mill and the HPGR and the stirred mills that weren't really used in Bond's day. And so to avoid this pitfall, and Morel was the first one to look at this, I think, was we can use the F80 of the primary crusher product and the P80 of the cyclone overflow because they're parallel in log-log space, and then calculate the sag mill specific energy separately and use the difference between the sag mill specific energy and the circuit specific energy to calculate the ball mill specific energy requirements. So that's typically how, well, that's what a lot of calculations do nowadays. There are still some calculations that you'll probably be aware of that still do use transfer size, but and they get around this in a multitude of different ways. So this really shows the reason why we can't use the transfer size for the sag mill. So if you do use that transfer size and you calculate the operating work index using the Bond formula that's on the top right in this slide, you can see what happens. These are 7 surveys of one concentrator at different points in time and different operational points. And you can see what results is that the ball mill looks like it's very energy efficient, and the SAG mill looks like it's very inefficient. If you use that T80, the SAG mill looks like it's expending a lot of energy for not much reduction in comparison to the ball mill. And that's the issue around using that 80th percentile passing for SAG mill products. So yeah, 3 times the energy or more in this way of looking at it. So yeah, this is what I was saying. Using the T80, this is what it looks like. One of the things I'll be talking to you about in this talk is using the fines production instead. So at the fine end of the size distribution, that is typically more closely related to the surface area production. The surface area of the fines is much greater than the coarse end. And if you look at Ridinger's theory that energy is proportional to the surface area production, we can use this fines production as a proxy for surface area. There are, you might ask, why don't we use surface area? I found it difficult to measure surface area. There's a multitude of different ways of measuring it, and the measurement of surface area is dependent on the way it's measured. Anyone who's looked at measuring the circumference of a continent or anything like that in high school, you'll remember that it depends on the actual size of the rulers that you're using as to what the surface area you get for a continent. Same's true of particles. So this is a simpler way and a more consistent way, I think, of looking at that. So if we look at I'll just go back to this. So the production of fines, we can look at the production of fines and look at that against the specific energy consumed, and that was called size-specific energy by Malcolm, who's on the call. So he kind of coined that term in 2010, but there's been many different people that have used it before. So we can look at Marco, who's also on the call, who looked at using the kilowatt hours per ton minus 75 micron. So in 2010, Musa, who looked at it, and prior to that, Levine, who produced a whole grinding test related to this. Schonert actually presented some data in this way in 1988. Mocken was in South Africa, looked at different mills, milling efficiency and discharge efficiency based on the production of 75 micron per specific energy. And Hookie also looked at this in 1968 when he was looking at the efficiency of ball milling. But the earliest reference to what we now refer to as size-specific energy was actually Davis in 1919. So well before Bond, actually. Davis, when he was looking at his fine crushing paper, looked at the kilowatt hours per ton of minus 200 mesh produced, and actually 200 mesh is about 75 micron. So this has a long history of being used. I guess I'm one of the newest converts to this, and someone that I look at this regularly nowadays, and I think it's even more important nowadays as the shape of size distributions is more irregular in a lot of breakage devices. So when we look at size-specific energy, I've got the equation on the top right. It's pretty easy. Specific energy divided by in this case, 75 micron generated. So the 75 micron in the feed product minus the 75 micron in the feed. When you look at that same data that was presented before, where the SAG mill looked like it was, it consumed 3 times as much energy for size reduction as the ball mill. When we look at it in terms of size-specific energy, so the production of fines, they're actually on par with each other. In fact, there's 3 tests where the ball mill is more efficient. There were 3 tests where the SAG mill was more efficient or consumed less energy for 75 micron production. And there was one test where they were essentially exactly equal. And this is what I've seen over a number of different surveys. This is just one data set. But there's been a number of different surveys where I've looked at this and found that in general, when the SAG and the ball mill are operating at similar efficiencies, that they receive a similar size specific energy, and they can be compared on equal terms using this measurement. So the other thing that you could do here, so the way you can present it as size specific energy, but the other way you can look at it is by plotting the 75 micron generated, or the percent minus 75 micron generated, against the specific energy consumed. And in that way, you can plot individual pieces of equipment and compare them against each other. So we can look at where the circuit sits here, and you can see that the SAG mill in this specific case consumed less energy to produce 75 micron than the ball mills did. So there's this potential improvement that you can see here if you're able to get the ball mills to produce a similar amount of 75 micron for the specific energy consumption. But that's just comparing individual equipment. What I presented in this SAG conference paper that's referenced below is that you can actually benchmark this against the Morel or the Bond efficiency. So compare it against standard characterization techniques. And that gets you your final point here. And we can see what the potential then is of each one of these mills and measure the efficiency of those mills. Those arrows don't line up, unfortunately, but you can imagine what I'm saying there, and you can look at the paper for more information on how to complete those calculations. But for those keen-eyed observers amongst you, you might have noticed that I'd used 75 micron in this example, but actually the hydrocyclone overflow, we're not in the linear component of that size distribution. We're right in the shoulder, and we're above 90%. It's never a good idea to use a marker size that's above that 80% of the final product. As Bond noticed, the size distribution does tend to roll over above 80%. So when you use the marker size that is above that 80th percentile, it does result in incorrect results, I guess, as most of the surface area as well as is in the finer proportion. So there is nothing magical about 75 micron. It was used in all of those publications that I referenced earlier. That's because it is very useful in typical plants, but it isn't. There's no magic about it. And actually, what I found is that using the P80 of the final product, the cyclone overflow, you can actually look at the percent minus P80 of the SAG trommel undersize, and that actually changes the mathematics of the equation, and you can have a measurement for the ball mill that is independent of the SAG mill. I said earlier that typically we do our sizing. We look at the total specific energy and we minus the sag mill specific energy. If you use this percent minus P80, you can have an independent measure of the ball mill specific energy. And I published that in this paper that's referenced down below in last year's comminution conference. So have a look at that if you're interested. But just to show you how that would work, here's some data from Saucedo, and that was collected by Juanjo, my student at the time, and myself in Mexico. And here we didn't use 75 micron, we actually used 53 micron. That was a better measure for this particular plant. And here you can see the sag and the ball mill. Similar, we had 8 surveys, and they had similar performance across the site-specific energy. But there were differences in the different surveys, and those could be explained with different operating practices there. So we can change the marker size, but the other thing that always concerned me or interested me was if we pull those into log-log space, which we're now in here, what happens if we include the gradient at that point where we're looking at the marker size? So I started trying to look through this. I haven't actually, I guess this is the part where it's more research, and I don't have any good conclusions, just some interesting trends that I've noticed. And this is the point where I think a lot more research could be done, and I hope it is done, and that maybe people in the audience take this up. But if we look there, not necessarily at the gradient, but at different marker sizes. What if we use 75 micron, 53 micron, 38 micron? We use a whole range of different marker sizes. We can look at the site-specific energy at multiple marker sizes. So if we go back to that Saucedo case that I was talking about, we can do the site-specific energy at multiple marker sizes. So if we look at the sag and the ball mill alone, this is the first survey. The ball mill consumes more energy at the 53 micron than the sag mill. And if we look at a multiple different marker sizes, you can see this this trend starts to develop for the sag mill. There's a linear trend in log-log space, and the ball mill has this linear trend up to a point where it starts to roll over. And that's because actually at that point, it's an incorrect marker size. So this is when we go beyond that point that I was talking about where above P80, the size distribution starts to roll over. So this is a good way of also working out where an effective marker size would be. But looking at the different marker sizes, and you can compare the sag and the ball mill once again at multiple marker sizes, and they have a similar relationship, and they're parallel in log-log space. Now that was one case. We looked at, there were multiple surveys. One of them was low density in the ball mill. That's why the ball mill was underperforming in this case on the left. When we actually reduced the water into the ball mill actually outperformed the sag mill at that reference marker size, the 53 micron. And we got a similar relationship here where there was this linear section. There was the incorrect marker size where we got that curvature of the ball mill. But actually the gradient of those lines were very similar, and were very similar to the ones originally in the other survey. So this got me thinking, I wonder if there's something that this is telling us about the actual ore that we're working with. And this is when some work that Dion, who's also on the call today, started coming up in my head. He has always been interested in fractals, and he can explain this much better than I can. But for those who are interested, there's a lot of work that was done in the 90s on fractals, and determining the fractal nature and of fracture. And you can see with these different images here, particularly the one on the bottom right, these are fractals that are generated mathematically, and they look very similar to a branching crack in rock breakage. So there's a way that we can describe the size distributions that relate to the fractal nature of the fracture that was occurring. So Turcotte in 1986 looked at this, and this is a graph just looking at the I think it's number of particles on the y-axis, and Dion can jump in and tell me that I'm wrong here. And the radius of the particle is on the x-axis. And when you plot it in that way, the slope of the line for these different ores gives an indication of the fractal the fractal size. And I'm getting the terminology wrong here because it's been a while since I've been looking at this. But yeah, so that size is looked at there. The fractal dimension, however, when we turn this into percentage passing or mass percentage passing with size, the slope of that size distribution is actually 3 minus the slope is actually the fractal dimension. So when we looked at Bond's work, he was saying that slope is typically 0.5. Well, yes, it is. And you can see that here, the fractal dimension of a lot of these mineral samples was about 2.5. That would equate to 3 minus 0.5 is about 2.5. So that would equate to what Bond saw in his crushing and rod milling and ball milling surveys. So that got me thinking, how can this size-specific energy at different marker sizes somehow relate? Does it somehow relate back to the fractal dimension? And what I actually found was, yes, it did. So I looked at a number of databases. I was doing the SEEK work at the time, and you could look at the size-specific energy against the marker size. And it actually, in this case, when you do the maths, the fractal dimension of the fracture surfaces, it was 3 plus the slope. You can see that it goes in the opposite direction from what we were looking at earlier. So that's why it's plus the slope. And when you looked across this database, I saw this very consistent slope turning up. And actually, across the database, they were very similar. And I could have a look at the distribution of that. So if we look at the distribution of all those data that we saw there, the fractal dimension of the fracture surfaces range from 2.5, which actually represents Bond, up to this 2.6 and possibly as high as 2.8, which is actually the Morel area. So if you look at Morel's initial gradient term that he coined in some of his work, that actually relates to this 2.5 to 2.65 region. So I thought this was interesting, and I thought it was a way that we could maybe describe these size distributions, and it does tend to be ore specific. I've found a lot that has said this is ore specific, but it's also equipment specific. And I'll show one of those scenarios at the end, just with some new stuff that I've done more recently. But yeah, that I think has a long way to go. I still can't explain it well, so I don't think I'm going to be the one to take it forward. But I think this should be picked up and used in research, and someone should look into this in a bit more detail. So I'll now go into some recent examples of using this. So one is coarse stirred mills. So I presented a paper with a couple of colleagues at the Mill Operators Conference last year that looked at coarse stirred mills and the efficiency of coarse stirred mills. And what I found, the example on the right here is a survey of a stirred mill following an HPGR. And if you took the final slope, the actual size distributions there, the stirred mill was operating at about 68% efficiency in comparison to bond. However, when you looked at, sorry, this is advancing a bit differently from what I thought it would. When you looked at the same slope, actually that resulted in a much lower, the higher efficiency in comparison to bond, reduce the effectiveness of that stirred mill. And the example on the left here is a tertiary stirred mill. And when you looked at the actual size distributions, the stirred mill was actually sharpening the size distribution. If you looked at the same slope as the feed, the efficiency of that mill effectively reduced when you looked at the P80. So what I realized there was that stirred mills actually sharpen the size distribution in comparison to the sag mills that I was referencing earlier. Stirred mills actually sharpen the size distribution, but it still means that we should be looking at this slope of the size distribution, and we should be looking at the fine marker size as well. Another recent example, this is actually modification of test work. So we received these 2 rod mill tests. So we only had 2 tests, unfortunately. There wasn't much sample for a specific study that we were doing at Azenco. And there were 2 rod mill work index. One came back at 10.5 and one at 6.8. So there was a marked difference between these 2 tests. Now, which one should we trust was one of the first questions that came up. So I actually did the size-specific energy work on this, and I looked at the percent minus 300 micron in this case in the feed and the product. And that, when I actually did the size-specific energy of those tests, they came out exactly the same. So although the rod work index was different by about 40–50%, the size-specific energy was exactly the same. So I went, well, what's going on here? And it was actually, the issue was the difference in feed size. So test 1 had a much finer feed size. There's also this bimodal distribution, which is a bit of a issue as well. But test 1 had a much finer feed than test 2. And actually test 1, because it had a finer feed, required less revolutions to be able to get to steady state. So it had a coarser product when you looked at the fines production. The P80s were very, very similar, but the fines production then went away from each other. So that then allowed us to be able to design actually on 7.6 kilowatt hours per ton minus 300 micron. So we had a consistent basis to then design on, rather than this variable rod work index that you can see above. So that was another way of looking at size-specific energy. And this final one, back to fractals, and the differences between HPGR and stirred milling. You can see here in these test work, actually the stirred mill results came out with a much lower fractal dimension. So they tended to more bulk splitting, less crack branching than the HPGR results that had a much higher fractal dimension, that was much higher than the actual. It was still lower than the sag mill, but it was much higher there. So that was an interesting result, because it tended towards more, the HPGR tended towards more shattering or more crack branching. And this drove differences in the gradient of those size distributions. So yeah, it will also what we worked out was it also influences the relationship between energy and size, like Morel and Bond does. So there's another relationship that needs to come in there that looks at this. But yeah, there were some interesting results that came out of some work that I was looking at. And I think this is the final one, but this was looking at, this is actually only a couple of weeks ago, where the feed size distribution to a milling circuit had this bimodal size distribution. And I looked at two different ways of assessing the effective P80 of that size distribution, because if I use the real P80 out at 4 millimeters, it would result in issues like I showed in the SAG milling work that we had earlier. So I looked at extrapolating up from the fines, the linear section, to where that crosses P80, and simply going down there, and that resulted in 1.6 millimeters. And actually the exact same effective P80 was found by doing another approach, which was describing this size distribution with two parallel size distributions with different P80s, but the same slope, and different mass splits. So I fitted the mass split and the P80s of those two size distributions to minimize the sum of squared errors. And that resulted in the exact same P80 1.6, effective P80 1.6 millimeters. So there are some, I don't know whether this will always be the case, but it was in this case. So I think it's another way of looking at bimodal size distributions here. It kind of reflects what Morel's done in the past and what others have done in the past as well. So nothing really new here. I just thought that would be an interesting way to finish it. So I'll finish there and open the floor to questions. We've got about 20 minutes, I think. But yeah, if there are any questions, please shout out.
Just unmuting myself, yeah. Okay, thanks, Grant. Nice, insightful piece of work, and really gives us a feel for the engineering side. Having left the research side and been on the engineering, the question was how to apply it. So we've got Marcelo, of course, is first up with a question. Over to you, Marcelo.
Hey, hello, Malcolm. Hey, Grant, before anything, welcome to GCC here officially. Very nice to see your presentation and you on the floor, so excellent. And so basically, I just have two comments. And the first is yes, I think it is always good to go back to Bond and show how careful he was when he actually said it's going to work, but it's under these circumstances. So it is very good, because a lot of the times that we see in the literature, people saying that I applied Bond's method and it was a disaster. You can see that they actually went to conditions that were far from what Bond said they were the optimal. So it actually means that Bond wouldn't have used those. And I think Steve Morel just pretty much narrowed that down a little bit further, tweaking things around, but still with those kind of careful thoughts on how to use the single marker. Because of course, people like ourselves who do advanced modeling, we love to start saying that Bond this and Bond that, limitations of using a single marker. But we do appreciate that there's value of looking, as you say, from a distance, the whole process, and understanding how the different machines contribute to the outcome. But that has to be done very carefully and understanding the limitations. And in some ores, that can be very tricky, the way particles break in the fine and ultrafine size range. And some of course, copper ores and gold ores, which make up a lot of the databases, sometimes are fairly well behaved. But when you look at like for instance, iron ores from Brazil and UG2 ores, they have kinks because they have funny mineralogies, and those things start to be kind of that's kind of weird depending on where you are in the size distribution. Things get bimodal, and as you said, so it actually, I think it means that we need to be careful of opening the black box when it's needed, and going back to simplicity when it's really possible. And I guess just a final comment in that, yes, I think that stirred milling example you showed, coarse stirred milling, is perhaps a very good example on when the black box should be open, because in coarse stirred milling, the internal classification is very important. And that size distribution becomes steeper, probably of the effect of this internal classification that you don't see if you grind finer or if you grind in a ball mill. So it also said that, guys, there's opportunity to open this black box here shouting at you. You might as well really look into that, because it's the process already, like Ballantyne. It's telling you that there's complexity in there that we already know about. That's going to explain why it's steeper or it's actually shallower because of the internal operation of the machine. But I think it's really nice to see this contribution on, yes, we can use these, but be careful on these and that. Very good.
I could discuss this with you for an hour, I think. I'm violently agreeing with most of what you said there. So yeah, so the coarse stirred mills, definitely classification. There's three lots of classification that occur in those verti mills. You've got the internal classification in the machine, but then also there's cyclones, and then there's also the they've got that external classifier that sits off to the side. So there's multiple different ways of classification selection happening there that lead to that sharpening size distribution, and I see that in a lot of cases. And I think that's what's responsible for a lot of the work that's been done in stirred mills, showing that there's this great efficiency improvement. It's one of the things that concerns me when so I'm doing a lot of work on hydrofloats at the moment, and the concentrate for hydrofloats can have a slope up to 1.5, so very steep slope, no fines. So any regrinding on that is actually going to flatten off the size distribution. So you can't use those same efficiency factors that have been developed on standard operations where the slope is actually increased with the stirred mill. So that's one side. Another side, you talked about different ores. A lot of that work that I showed there is actually on graphite. We've been dealing with graphite a lot recently. And that obviously has not just breakage, different breakage and different components in there with different hardness. It also has shape that comes into play whenever you're screening it. So there's all kinds of complexities that come into there that create all kinds of weird and wonderful perturbations of this. So yeah, thanks for your comments. I violently agree. So that, I think Dion's got his hand up now. I don't know.
Dion, I'm sure it'll be a follow-on. Thank you, Dion.
Yeah, well done, Grant. I really enjoyed that presentation. I think that's probably the best one I've seen you to deliver. It's great to see you grappling at the very edge of knowledge while keeping it real, if I can put it that way.
Thank you.
I've got quite a lot of comments and things that we'll talk about otherwise, but I've got a question to Marcelo. What do you do once you open the black box? But I'll let him answer that one later. The other comment I wanted to make was that with regards to fractal dimension, it's pretty clear that the old boys, long before the mathematicians figured out what fractal dimensions were, and Mandelbrot formalized that in his famous work, the Fractal Geometry of Nature. Guys like Bond realized that looking at size distributions in a log-log plot made some degree of sense, and looking for straight lines in a log-log plot tells you something. And Turcotte was the one that really made it clear that the slope of that line of the percent passing distribution on a log-log plot tells you about the geometry of the fractures that form the fragments that produce that distribution. And that is really fundamental. We should never be plotting size distributions linear log. Plot them log-log and look for straight lines. And where you see a break in those straight lines, you're seeing a characteristic size that's either related to the ore or it's related to the equipment. So that's just my little comment, Grant, to add to what you said about fractal dimensions there. Otherwise, I really liked that last bit. I really liked how you broke that distribution down into the coarse and defines, and I'm looking forward to talking with you more about that. So well done, Grant. Really, really enjoyed it.
Thanks, Dion. And I think there's a lot to take away from the work that you've done and showed me in this area. So thanks for being open with your knowledge with me as well. That's been it's been really interesting learning from you. In terms of plotting things log linear, I feel like I should raise the relationship that we stumbled across with Shujat the other day, where we plotted it. He's doing some work on rolls crushing, and we plotted the gap of the rolls against the specific energy consumed by the consumed in the breakage, and we saw a linear relationship between in a log linear plot. So there was a logarithmic relationship. Once again, it might be going back to Bond and those old timers. We saw a linear relationship. We have no idea why. But it's interesting, and maybe something will come out of that that advances knowledge. So yeah. Anyway, I just thought I'd raise that since you got you on the line there, Dion.
Yeah, fair call, Grant. I think whenever you've got new data and you're exploring it, it doesn't hurt to flip the log toggle on either axis and see if you can see straight lines, because it'll very quickly lead to a potential model for the data. And then the question is, why is it that model? But when it comes to percent passing versus size, log all the time.
Always.
Because Don Turcotte has told us how to interpret that.
Yep.
So I'm going to jump to, Brian had a question in the chat of, have you got any data in your database of ag mills? You didn't show any ag mills.
I haven't shown that. Yes, I have done work on ag mills. And what I found is that fine end of the size distribution tends to have a characteristic slope, but that the rollover kind of changes. So the T80 changes related, and the throughput changes related on the amount of ball. So just in general, the ball load, the rock to ball ratio. But I haven't done a lot of work in that area, unfortunately, Brian, so I can't comment too greatly. One thing that I have done recently that I think every comminution person should be aware of is that I did some greenhouse gas emission calculations that take into account not just the steel media consumption, but also the steel in the construction, so the structural steel, and also the steel in the mill shell and the copper, all of those kinds of things. Took all of that into account, and it was the first time where I pulled all of that information together. And you know what I found that I thought was very interesting and tells you a lot is that it takes 6 weeks for the mill to consume the weight of the structural steel and the mill shell in ball media. So it takes 6 weeks for the mill to essentially consume all of that steel that you see around a grinding media in a grinding circuit in steel balls. It consumes itself 7 times per year. It's just astronomical. I never pulled them together on that basis, but once I started seeing that, I realized, wow, we should be doing much more in the media consumption realm. We should be designing mills with larger shells, still the same size motor, but larger shells so that they operate at lower ball loads. We should be looking at ag milling and pebble milling as viable options it's back to the past, I know, for a lot of people, but we need to be looking at that for low OPEX plants and low greenhouse gas emissions associated with the plants. It's just something that needs to be incorporated into the studies that we do, and we definitely do that where appropriate and where that's going to add value.
That's a good description of that process, because I'm doing a project right now with a large company that's doing it for exactly the reason you're saying, looking at ag mills. It also highlights from the seminar, if we put a few more of our databases together, I have quite a bit of ag milling, and I know Aubrey does, is that we can extend that bit of work, things like the different modes of breakage changing the fractal, and understanding that a bit better, because it would really help the industry grasp the opportunity of how that changes. You go from high ball load bag to sag to low ball load to ag, and where it works for you. Because I found, so to answer Brian, I found in my data the ag mills are really efficient, so a good size specific energy, but their drawback is they can produce too much of it. So actually you get a finer product than you need. And I did present that in SAG conference, the last SAG conference. I can comment. I'm in Sweden, quite near the Aitik mine, which is, was the biggest ag mill in the world. And they actually have that problem that it's very efficient, but they are producing more fines than they require. And you can't stop an ag mill doing that. So they're very strict. You can crush some things to reduce the fine grinding and push it through the circuit. So those have to be put together when considering it, but it's lacking in the understanding of the way it's applied in the industry. It was seen as being less efficient. It's not. It just does more work.
I think there are some reasonable comments around that in terms of the operability as well. I remember SAG conferences where people presented when their mill was changed to secondary crush feed, pre-crush, and they said it's never been easier to operate. It's just been like a dream. You don't have to worry about it. It just goes around and tumbles, and there's no impact of all variability and all these kinds of things. And so you look at that and you go, well, secondary crush feed makes it easier to operate. SAG mills are less easy to operate. They've got more variability. Ag mills are much harder to operate in terms of operator comfort, I guess. So that's one of the things that obviously has to come into play there.
Yeah, we could have a 2-hour conversation on that. I can operate ag mills really stably if the plants is well built. Yeah. I think, Marcelo, you had a second question, did you? Or?
No, actually, it was not a question. It was just a comment right after Dion's, but I kind of missed the point there. But it's really out of curiosity, which is when I work with Leonard Austin, which you all have well heard about him, back 30 years ago, he was one of the guys who actually came with the ruler every time we started discussing, because he wanted to see exactly the slope of the lines that I got in the experiment. So he said that if it doesn't look like it's natural, I won't even talk about your experiments because there's something wrong about them. So it is something that a good message following yours and Dion's point, which is, I think sometimes we really go straight into modeling, simulation, parameter estimation, selection functions, and so on. And we don't really take care of looking at the data and see that, does it seem natural? What is probably going on in the background? So just a curiosity there.
Yeah, I found that Greg Lane does the exact same thing. Whenever you send him a size distribution, he sends it back, and he does it really simply. So it's probably a good trick for those who want to look at it. if you have a log-log axis, you can get that slope of a half just by going from by looking at that log-log axis. So if the x-axis has 10, 100, 1,000, that's 2, and then you go up 1 on the y-axis, and you can draw a straight line. It's a slope of a half. So it's a very simple thing you can just do with a ruler, or in paint, or insert a line into the graph, and that just gives you an immediate test on that. And it's one of the reasons why, as Dion said, you should always be plotting your size distributions in log-log space, because it gives you a good indication of what's occurring there.
And if I might add, it also gives you a way to cry bullshit on models that claim to be predicting the product size distribution. If they don't have straight lines in log-log space, as Marcelo was alluding to, it's probably not natural.
And also blasting models. Blasting models are very good at doing that, of under predicting the find. A lot of blasting models and feed size distributions to crushing plants should always be, a ruler should always be run over them, to make sure that they got that slope of a half.
I might ask my question, which was to pick quite early in your presentation, using the delta energy, calculate the circuit, put the sag and the ball as the difference. And you said, therefore, you don't use T80, but I'd say that's an incorrect statement. You've got an embedded assumption about the transfer size there because you're not measuring it. So Muriel, from his database, said, oh, this is the kind of transfer size I get. And he's plugged it in, 0.7, I think it is, millimeter.
1.7.
1.7, sorry, 1.7. And different mills are really different. So I think it's flawed. It's ore dependent. If you know the ore, you get the answer right. But it's still in there. It has to be in there, is the size distribution. And it's the database that's staring back at you. You might have a comment on that, but
yeah,
I've kind of avoided it for that reason.
So I published a paper at the Comminution conference last year where I looked at exactly this. So I used percent minus P80 as a descriptor of that transfer size. So I wasn't using T80. I was using percent minus P80 of the cyclone overflow as the transfer size. Then I looked at the mathematics that sit behind that, and you can take away the sag mill specific energy from the total specific energy and work out what the ball mill specific energy. Then you can back calculate from the ball mill, if you have that P80, what the percent minus P80 and the feed to the ball mill would need to be to get that P80. And that allows you to go from both directions. So you get the sag and the ball, and then sometimes they don't meet in the middle. So you need to modify that transfer size until you get to a point where the sag specific energy and the ball specific energy meet, and the transfer size makes sense between the two. So that's something we've incorporated into Osgrind more recently, and it's less of an issue for, I guess, what you would call standard ores, where the A times B and the bond work index are related in a reasonable regime, but sometimes the A times B might be much higher and the bond work index is also high, or the other way around, the A times B might be very low and it's very coarse ore competent, but the bond work index might also be very low and it's actually quite easy to mill. And that's when it starts to fall apart, and these kind of estimates start giving wildly different numbers, giving different estimates. So that's why we've looked at that method for the percent minus P80. Yeah,
because it is, in essence, if I use my own terminology, it's using the size specific energy and saying if they have the same efficiency, that's it, and you get array from the database. So I like your answer because it is the way to escape it. Bearing in mind that if it's essentially bimodal, you have to know that the SSE is actually changing because you've got a different mineral structure. Your fractal dimension will change. So that's the warning light on any of this.
Yes, much so.
Well, thank you, Grant. I think that's been really enlightening. I'm sure the people who've been on have really can take home something useful from that. And it's also, I'm very pleased you gave it as your kind of introductory talk in the GCC. It's because it's such an integrated set of work across the group. And I think as a group, we can build on that some more and put our data in our heads together. So thanks, Grant, and for taking our original research out into the industry. It's very good. And we hope to catch all of you at our next seminar.
Thank you. Thanks, everyone.
Malcolm, Brian's got a burning question if we've got enough time for it.
I didn't spot that in the chat.
Sorry, I'll answer that quickly. Yeah, Brian, what I was actually saying there was that if you pre-crush, you'd move to a bag mill, so barely autogenous mill, so you'd have to have very high ball loads. So you move further away from ag milling when you pre-crush. So that's what I was referring to, and that makes operation easier because the size of the feed isn't influencing the ball loaders as much because the balls are doing all of the work.
Okay, great. Cheers, everyone. Thanks for joining us.
Cheers. Thanks.
Hey, bye, everyone.
Thanks, everyone. Bye.